All right, let's get started. So today we're gonna kind of continue on our journey through Bayesian filtering. We're gonna try and instantiate Bayesian filtering for our race car, try to go through some of the models, and this is going to be important for homework 1, no, homework 2. Yeah, a lot of these things are also on the website, but I think we should go through them in detail, right? So let's do a little recap. So we discussed Bayesian filtering. How do we feel about Bayesian filtering now? Rich? Okay. Can't spend another lecture on Bayesian filtering. So you all should come to see me in office hours and I'm happy to discuss it again. But the tutorial I went through on the iPad is, I think, helpful. And so maybe go through that. But the basic idea, just a quick recap, is you want to figure out a way to tell what the current probability of over state is given a history of measurements and actions. You're going to start from a belief at 0 and then alternate between 2 steps, the prediction step and the correction. And the prediction step says take the previous belief multiplied by the motion model or the transition model, so that's how the word moves. So it gives you belief bar, and then belief bar is going to be corrected through measurement. So you're going to say take belief bar multiplied with our measurement model gives dt given xt, renormalize it, and that corrects your belief using additional measurements you take in the loop, right? So you move, correct, move, correct, move, correct. That's the basic. Now, that's the basic concept of Bayesian filtering, but all of these things are still extremely abstract, right? Like, how does this connect to a race car? These are just symbols. And so what we're going to try and do today is we're going to try and instantiate the elements of a Bayesian filter in the context of a race car. And so we're going to say, we're going to try and define what state is, define what measurements are, define what actions are, and then try to define these quantities, which is the transition model, right? And the sensor model. And once we define the transition model and the sensor model, then you can apply a Bayesian filter to your race. And so what we're going to try and do is be very concrete about the form of this and this. And that's all we want to get through today. Try to define what P of xt given ut and xt minus 1 is, right? How does the word transition? And then how the sensors behave, right? Specifically for the race car with the LiDAR. Okay. So in the context of our car, we're going to have a race car. The race car is going to, at any point in time, it's going to move to a new state. Because there's going to be uncertainty in things of the race car, initially, the race car could have been in some set of places. When you move, there will be additional uncertainty. So the set of places is bigger, right? And that's going to be your prediction step. And then you're going to try and have a correction step, right? And the correction step says, okay, I shoot this LiDAR, the LiDAR receives some readings, and so the readings kind of can help me correct for it. And so imagine you had a belief that you were in all of these places, but the LiDAR is kind of inconsistent with this and this. So it kind of cuts off those places and helps you narrow your belief of where you are, right? And so in the context of the race car, there's uncertainty because of motion, and you reduce uncertainty because of that. And that's going to be what we're going to instantiate today. And so we want to define these two quantities, the motion model and the sensor model. So let's start with the motion model, right? So the motion model just says, here's my race car, here's the action I take, what is the distribution that I'm going to be in the future, right? And how do we get that? We're just going to use physics, right? We're going to treat this as some sort of rigid body motion, and we're going to use physics. And we're going to derive the motion model with some uncertainty. And so we're going to get P of xt given ut and xt. Okay, so we discussed this last time. You can choose how detailed your motion model is going to be. Right? You can be, a company like something that, F1 racing team and define an extremely accurate model because you need extremely high performance racing, or you could be like us and be lazy and define a simple model with lots of nodes, right? And so the idea is that this is way more computationally tractable. It's way more expensive. You need millions of dollars. I do not have millions of dollars. So we're going to use the simple model with lots of nodes, right? And the trade-off here is that the better model will give you a more accurate estimate, right? But the simple model with lots of noise will be cheap and still maintain uncertainty in a way that you can be robust. So for most applications, you want to use a simple model with lots of noise to make it track. There's also a potential con of using a high fidelity model. Is you use high fidelity model, but it's wrong, then you have catastrophic outcomes, right? You have like a high fidelity model with small amounts of noise, but it's just wrong. Then you will take the incorrect actions with high confidence, and you crash your car when you're back. Okay, so we're gonna try using probabilistic motion models, and we're gonna try using stochasticity to make up for our laziness, right? So we don't want to model everything about slip and actuation and all the other errors. We're gonna use stochasticity to cover all of those. And so we're not gonna get a single point estimate. Like in your homework, you'll see the car's not at one place, it's going to be over some spread of places, and that place, the distribution of places that it might be in evolves over time. Right? And that's important, less in simulation, more in the real. Okay. Does this make sense so far? Are we following what we want to do? Any questions? I guess I didn't really say anything of substance yet, but does the premise of what we're going to talk about today make sense? Yes? Okay. So we want a motion model that's able to explain any measurements we're going to see. So we want it to be somewhat accurate, right? But we want it to be able to deal with unknown unknowns, right? So we want to be able to figure out, okay, we don't know what the slip is going to be on the carpet. We don't know what the delay is going to be. We don't know what, electronic issues we might have. And we want your uncertainty to capture all of that. So you need to make sure your motion model is not capturing known unknowns, it also capture unknown unknowns. And last, we want something that is running in real time on a race car with not a very powerful computer. So we want it to be computationally quick and efficient. If you have an expensive model, then it's an expensive process to run through. So those are the criteria for our motion model. And so we're just going to have a simple model, which is basic physics. You're going to see that the physics are completely wrong, but they're going to be good enough for us to do good enough for us to do Bayesian filtering, right, to figure out where you are. Okay, so specifically, what we want to do is a kinematic model. Right? So kinematic model tells you how robot velocities and steering angles affect future positions. We don't want to do a dynamics model. The dynamics model is something that tells you how, currents or torques on the wheels, how forces affect motion, right? So dynamics are about forces, kinematics are about velocities and position, right? So we're just going to deal with kinematics for now, and in 2 to 3 weeks, we're going to cover them. The dynamics are more difficult, but we're going to assume that the wheels don't slip, right? So you're not sliding around, you're not drifting. Drifting is hard. So we're not drifting, no slippage. And so we're just going to cover kinematics. Yeah. And we're going to directly actuate the velocity and steering angle. We're not even going to touch things like motor torques. Yeah. Okay. So let's get straight to it. Right. So what we want is to define this model F, right? F takes in your current state X, your action U, and tells you what is the rate of change, right? So it tells you what X dot is. X dot is dx by dt, the derivative. So what you want to define is how does X and U map to the change in X? What is the change in state? Now, what is X and what is U for a race car, right? For a race car, X is going to be the state, which is the current X coordinate, the current Y coordinate, and the heading. Right, so you want to say, okay, if your race car is like faced at an angle, what is the X and Y, and which way is it pointing, right? And what are your actions? They're going to be velocity in a straight line, like how much velocity you're going to apply to the wheels and your steering angle, right? So your velocity is going to be V, and you're going to have your steering angle there. And so to instantiate this in the context of the race car, we're going to say X is XY theta, U is V and delta. Right, and we want to figure out how does X change given a particular XY theta and a particular V and delta. Does that make sense? Now, this is going to be a derivative, right? So here I've defined this as a derivative. And derivative is the instantaneous change. We're going to operate in discrete time. And so we're going to like convert this derivative into, a change in X. And so earlier we had talked about our motion model as, this, xt given ut and xt minus 1. You can see these are discrete time steps, right? And so what we're going to do is we're going to take our derivative and just like do numerical integration to get it over some time. So the derivative tells you something at an instant. We're going to figure out what the change is and then integrate it over a bit of time to get what the next step is. Okay, so what we've talked about so far is we have a system of xy theta, we have actions that are d and delta. We want to figure out what the change in xy and theta is going to be. Right? Okay, so once you have that, you can then figure out you had your previous x, your previous y, your previous theta. Once you know x dot, you can figure out what delta x, delta y, delta theta are going to be. And then you can figure out what the new x, new y, and new theta is. And so your motion model tells you, given a particular action, what is the change in x, what is the change in y, what is the change in theta. But we want the models to be noisy, and so we're going to add some noise. Right? So we're going to say, we're going to take our motion model, which is going to be from physics, get changes in x, y, theta, and we're going to add some noise. And in your homework, you're going to add noise in two ways. You're going to add noise after you compute the next positions, and you're going to compute a bit of noise on the actions. Right? So you're going to say, you fed in some actions, you're going to add noise to the actions, and then you went through physics, it gave you some outcomes, and you're going to add noise to those outcomes. Right? And so physics will tell you this, and you're going to add noise before, and you're going to add noise after. Does that make sense? Everyone following me so far? Any questions? Okay. So let's maybe try to see if we can draw this out a little bit. But in order to figure out the physics of the race car, we're going to start with this concept called the instantaneous center of rotation. Right? So the idea is that if you have a race car, I'm just going to try drawing on my iPad again. If you have a race car, right, it's not just going to go in straight lines, right? It's going to go in straight lines and then also potentially rotate, right? So it's going to be doing a rigid transformation. It's a rigid body, right? And the rigid body is going to have some amount of rotation and some amount of translation, right? But a nice property of rigid bodies is that when they are doing some sort of rigid transformation, you can view it as a pure rotation about a point, which is called the instantaneous center of rotation. And so let's try and understand this in a different body, okay? So let's say this is our body and it's undergoing some like rigid transformation, right? There's going to be some point which doesn't rotate. Right? So imagine that this was like going through some translation and some rotation. At that instant, there's going to be one point on the body which doesn't rotate, right? So it's like, imagine that you had a body like that was doing some rigid transformation. At any instant, there's going to be some point on the body that doesn't rotate, right? And that's going to be the instantaneous center of rotation. And so this is easier to see in this kind of body that I have on the screen because it's in the body, right? So you can say that there's this point that's in the body and it doesn't rotate. It has no velocity. Like it's a point that's at rest, right? And so you can think of it as like, it's almost like rotating around this point. Now, if it's like a rigid transformation, then it's both translating and rotating. So the important thing to remember is that this is only true at that instant of time. And then another instant, the position might change, right? And so that's why it's the instantaneous center of rotation. Does that make sense? It's a little bit non-intuitive, right? But it's like in this body, it makes sense, right? It's inside the body. In other bodies, it may not be inside the body. So for this L-shaped thing, for instance, right? It's moving, but the instantaneous center of rotation doesn't lie in the body. And it doesn't have to lie in the body. It's some point in the plane, right? And the instantaneous center of rotation is going to help us figure out how to move things, right? But this is just like a simple concept from physics. It's saying that at any point of time, there exists a point which has zero velocity instantaneously. Okay, so how do you find the instantaneous center of rotation? Let's say you knew that there is this point that is moving like this. You knew that there was this point that's moving like this. Right? Can you all think of ways to find the instantaneous center of rotation? Like intuitively, this is moving like this is moving like this. Like that's probably the instantaneous center of rotation, right? It's like the point which doesn't move. So how would I find this point? Yeah. Yes. Perfect. So you take perpendiculars to the velocities at both points, right? So you can say take the perpendicular at this point, take the perpendicular at this point, the point at which they meet, right? is going to be your instantaneous center of rotation. And if it was not a rigid body, this wouldn't hold, right? Because the points might change relative to each other. But for a rigid body, everything remains at rest, right? And so at any point of time, you want to find the instantaneous center of rotation, take 2 points in their velocities, draw perpendiculars. The point where they intersect is your center of rotation. Okay, so for this, you can see for this figure right here, right? The velocities VC, VA, and VB are moving in different directions. You draw the perpendiculars, and that's what gives you an instantaneous center of rotation, right? And that's why it lies outside the body. Are you following that? Okay, great. So why is the instantaneous center of rotation useful? So it's useful to define this model that we're going to call the kinematic bicycle model, right? So the idea is that we're going to almost treat this car like a bicycle, right? Because there's no slippage, right? So you can almost treat it like a 2-wheel system, right? With the front wheel is like a bicycle, you can rotate it. And so let's try and figure out what's happening here, right? So this car is, let's say our point of reference, the thing we're going to measure is the rear axle, right? So the middle of the rear axle. And so let's say its position is X and Y, right? And let's say the frame of reference of the world is like, those are the axes, right? And so the angle of the car with the frame of reference is theta, right? And so the state of the world is X, Y, theta, right? And then you want to say that you're going to apply a velocity V, right? That's going to tell you what direction, what speed you're moving with. And you're going to apply a steering angle delta. Yes? Okay. So what this is going to do is it's going to, the car is not going to go in a straight line. It's going to move in kind of a circle. So to figure out where you want to be, you want to figure out the instantaneous center of rotation, right? So to figure out the instantaneous center of rotation, because there's no slippage, you're going to notice that this point right here moves like that, right? There's no slippage. And this point, because you turn the wheels, is going to move like that, right? And so how would you find the instantaneous center of rotation? And so you draw the perpendicular here, you draw the perpendicular here, and that gives you the instantaneous center of rotation, right? And the important point is that this is 90 and this is 90. Yes? So all we've done so far is define the variables of the system and found the instantaneous center of rotation, right? And let's call the length of the vehicle L. Okay, you know this, it's a race car. And let's call the distance to the instantaneous center of rotation, let's call it R. Okay. And so now what you need to figure out is what is the change in X, what is the change in Y, and what is the change in theta? Okay, right? Does that make sense? As a problem definition, like we've defined inputs and outputs of the problem. We are X, Y, and theta, the orientation. We're applying velocity G. We're turning the wheels by delta. This is the center of rotation that we found by drawing these perpendicular lines, right? This is R, this is L. L is known, R is not known yet. Okay? We'll figure it out. And we want to figure out what is X dot, Y dot, and theta dot. So I forgot how to do this, so you all have to tell me how to do it. So how do you get X dot? How do you figure out the change in X? You get some velocity, and you're trying to figure out like, what is the change in X position? It's not a trick question. How do you know the V, you know the theta. It's like, what is the instantaneous change in X? Yeah. V cosine theta, perfect. Excellent. X dot is V cosine theta. Okay, now what is Y dot? Just say it. V sine theta. Great. And this one is a little trickier, right? Because theta dot is you're trying to figure out what the change in angle is, right? And so this one is a little trickier. So how would we figure out the change in angle, right? So I'll help you out with this one. Basically, the theta dot is angular velocity, right? It's like how much is the angle changing. So theta dot, whenever you have angular velocity, right? There's like physics tells you that V is equal to R omega. So the velocity at any point is the distance from the center of rotation times the angular velocity, right? So the angular velocity is v divided by r. Yes? This is from like angular physics, like I don't know what the UW class is, but intro physics. Um, and so you have V by R, right? And that's going to be your change in angle. The problem is you know V, but you don't know R, right? And so how would we compute R? So R is just this length. You know theta, you know delta, you know these are 90. How would we compute R? Yeah, right. So the trick is you have delta here. This is 90, which means this is 90 minus delta, right? Which means that this is delta. Right, so this is delta, this is 90. These three have to add up to 180, right? So this is going to be 90 minus delta. Yes? Yeah. Now this is a right angle, this is a right angle triangle. This is 90, this is 90 minus delta, that is delta. Right? So the first thing we know is that angle up there is delta, right? So we know that this angle is delta. And now we're going to use the definition of tangent, right? So we're going to say tangent delta is equal to L over R, right? And so R is just going to be L over tangent delta. Yes? So now you know R, right? And you know that W is equal, or theta dot is equal to omega, which is equal to V over R. So is equal to V over L times tan delta, right? These are all known quantities. So you know V, you know theta, you know L, you know delta. Right? So you define the physics of your race car in terms of known quantities. Right? So you know how does X change, how does Y change, how does theta change. Yes. Yeah, because we're assuming no slip. Right. So it's not like drifting.
Also, so in practice, you can only turn your prep wheel.
Yeah. And if you had like the back wheels changing too, that like totally will mess up your but yeah, the no slip is what lets you say that this is 90 degrees and this is 90 degrees. Because you know the velocity of the back wheel will go this way and the velocity of the front wheel. Okay, so all we did is some basic trigonometry to figure out that x is going to change with v cosine theta. Intuitively, it's saying take the velocity and take the portion of it which is facing in the x direction. The y is going to change with v sine theta, right? And then the angle is going to change with v tangent delta by L because you find instantaneous center of rotation. Okay, so you can get rid of my handwriting, and we figured it out. Great. So that's really all that the physics of the race car is, right? So piece of homework for all of you is to say, like, we took our reference point, the point that we chose to define our x and y and everything with, to be the rear axle. You can also do it at a different point of reference, and then the instantaneous center of rotation will look different. And so you'll have to change the math a little bit. So homework for everyone is to try and work it out. You don't have to, but it'll be fun. But okay, so we figured out what is x dot, we figured out what is y dot, we figured out theta dot, right? And now we need to figure out how to change x, y, and theta, right? So we have to figure out these are derivatives. Derivatives are not telling me how much to change, right? So I need to figure out what is delta x, delta y, delta theta. Right. So whenever you have a differential equation and you want to implement it in practice, often the easiest way to do it is with numerical integration. And so what we're going to do is we're going to do some numerical integration. We know x dot, we know y dot, we know theta dot, right? And we're going to work out what is theta after some amount of time going to be, right? Okay, so you all are going to work it out for us, right? So let's say we have theta dot, right? And we want theta dot dt integrating from time t to t prime, right? So we're at time t, we're going to go to time t prime. What is this integral going to be?
gonna V by L tan delta dt from t to t prime, right? We're gonna assume that the steering angle doesn't change from t to t prime. There's like small period of time. So this is just gonna be V by L tan delta times t prime minus t, right? So it's just gonna be V by L tan delta times delta t. Okay, so that's the first one. That's the easiest one. Now let's try to figure out what is what is the so this is going to be delta theta, right? Now let's try to figure out what is delta x. Okay, so what is delta x? It's going to be v cosine theta dt, right? But theta is a function of t, right? So let's try to write this in terms of d theta instead of dt, right? So we know that d theta over dt is v over L tangent delta, right? Just from this. Yes? Okay, so we know that that's what d theta over dt is. So we can write dt is d theta over v tangent delta times L, right? Just move it to the other side. Okay, so we've just moved this to the other side, move this down here, right? And so we've written out dt in terms of d theta, right? So now you can rewrite this as v cosine theta times L times d theta divided by v tangent delta. Yes, just substitution. Okay, so these cancel. And you get, what do you get? L over tangent delta times sine theta prime minus sine theta. Right? Integral of cosine theta is sine theta. Right? And so you're just going to get L over tangent times sine theta prime and sine theta, where theta prime is computed using this. Yes? So we've said, all we did is we took these theta dots, x dots, y dots, and we integrated them over time. Right? That's going to tell you how much the change is over some amount of time. Okay, how do we feel about that? Confused? All right, let's ask some questions. Or let's do it again. So how about we work through it again? Right, so I'm gonna ask a volunteer. Tell me what to do. Remind me again. Yeah. Yes, Leo. Tell me how do you start it? Okay, so we're integrating. Why do we need to integrate? Because it's instantaneous, right? And you want to do it over some period of time, right? So we're just going to say we're integrating theta dot is the change in theta per unit time. You're going to say theta dot times dt, you're going to integrate over, right? That's going to tell you the change in. Okay, so you're going to take v over L times tangent delta, and you're going to multiply times dt, and then you're going to integrate it, right? So let's see. So you're going to have v over L tan delta, right? You're going to assume that steering angle is constant, right? So it doesn't depend on t. Steering angle remains constant, so v remains constant, L remains constant, tangent delta remains constant. So everything comes out of the integral, so that nothing is left in the integral dt. Integral dt with the finite integral is going to be t prime minus t. And so v over L tangent delta times t prime minus t to delta. Okay. So that's one. And then to get delta x, all you're going to say is you want to take the x dot and integrate it over time. Right? So you're going to say v cosine theta dt, you're going to integrate it over time. Now, problem is theta is a function of t. And it's like kind of annoying to do, right? And so instead, if we can just write everything in as a function of d theta, as nicer to integrate. And so we're just going to try converting that dt to something in terms of d theta. Right? And so we know that d theta over dt is v over L tan delta. Just gonna do a little bit of moving around, right? So we're just gonna say d theta over dt is v over L tangent delta.
you're gonna move this up, you're gonna move this down. And it's gonna give you dt in terms of d theta and v over L tangent delta, right? So you're gonna say dt is d theta over v tangent delta times L. You're just gonna substitute that back in over here, and that's just gonna give you your integral. Okay? So I encourage everyone to like go home, erase the board, and just like try to work the whole thing out from the start, from the instantaneous center of rotation to everything else. I think it'll help understand what's going on. Okay, but roughly this intuitively makes sense, right? So you're saying, okay, that was your angular velocity. This is how much it changes. This is how much your x changes. That's how much your x changes now. That's how much your y changes. So that's going to be your motion model. Are we done? Like, what is this enough, or do we need to do more? So we figured out how we've gone from the delta x tells me how to go from x to the next x, right? And same for y and same for theta. But is there more that we need to do, or are we completely done? Yes.
Like, what have we achieved in context by integrating? Because I know it was
Right.
instantaneous, so now.
Yes. So now we are gonna, what we're gonna have is we had x at t minus 1, right? And now we figured out some delta for like some period of time to go from t to t prime. So now we figured out that, okay, like that's how much each of these changes. And so you know, okay, this is how much you have to add to xt minus 1 to make it into xt. Same for y and same for theta. So this gives me a model that goes from xt minus 1 to xt, yt minus 1 to yt, theta t minus 1 to theta t. So what we've achieved is, how does the world move forward given some action, right? So if you would see, all of these things are in terms of current variables of state. So theta, v, right, and action. Delta, theta, x, y, and in terms of actions, which is delta and v, right? So you figure out in terms of current state and actions, how does the world change? Right. Okay, but you know, I repeated noise like 10 million times at the start of this lecture, right? So the important part is there's no noise in the system, right? And so for it to be a useful model for us, we need to make sure to add some noise, right? And so the important thing here is, okay, this gave you some future x's, right? And you're going to add some noise to it, and there's two ways we're going to add noise. The first way to add noise is we're going to add noise to the outputs. Right? We treated it like a deterministic system. This xt minus 1 went to xt deterministically. It's an equation, right? And then we're going to say we're going to sample Gaussian noise. And from some variance, we're going to sample the Gaussian noise, we're going to add some noise to it. Right? And so what we're going to get is we're going to say, imagine that you had a Gaussian centered around these things, and you're going to have some noise added to it from a Gaussian distribution. And then the other way to add noise is when you feed in v and delta as actions, you're going to add some noise to the actions before you compute the equations. And that's a little different than adding noise at the output. One of them is adding noise at the input, one of them is adding noise at the output. And then both of them will help you with your projects. So remember to add noise in both ways. Okay, so we've talked about this a bunch, but essentially the reason we want to be probabilistic, the reason we want to add noise is because we have a bunch of things we have not modeled, right? So for instance, we haven't modeled voltage as analog signal, it's continuous, but we've discretized it. We've had things that we haven't modeled about the slip and the friction and the issues with like gunk in the wheels and so on, right? Or battery, battery levels, etc. And so having some noise will make your model and your planning way more robust. So remember to add noise before and after. So add noise to control before propagating and add noise to the state after propagating, right? That's important. So essentially what it looks like is this was your car initially, that was your car at the end, you're gonna add some noise to it. And so it's going to give you some distribution of places you might be. Okay. So that is the first part of our lecture. That is the motion model, right? So to instantiate a Bayesian filter, you need a motion model and you need a sensor model. Right, so we're going to go over the sensor model next, but how do we feel about motion models? Yes. Good. Great. Okay, so the next thing we need to figure out is a sensor model, right? So in the sensor model, what we want is
a model of, what is the likelihood that I receive a particular sensor reading ZT, given that I was at some state XT in the world, right?
And we're gonna assume you know the map of the world.
And so for our purposes, you know where the obstacles are, you just don't know where you are in the world.
So we're gonna go with fixed map. We're gonna try and
Estimate where you are in the world, given the sensor readings from a LiDAR sensor. Okay? And so ZT is going to be sensor readings from a LiDAR, XT is going to be where you are in the world.
the same idea can be applied to like estimating maps too. But we'll get to that. For now, fixed map. So think about it, you know where you are, or you know where the world, you know the map of the world, you just don't know where you are. And the sensor readings will help you understand where you are. And if it is not a noisy model, it will tell you exactly where you are. But if it is a noisy model, or almost, and because it's a noisy model, we have to be probabilistic and use Bayes rule and all the good stuff. Okay, so what we're gonna try and do is we're gonna try to use LiDAR. So this is
Promotional video from Velodyne. They paid me for. And so you can see here that the car has like a LiDAR, and it's gonna try and detect how far away things are. So it's gonna essentially, most of these are like time of flight sensors, so they basically have a spinning thing which shoots out laser beams at high speed, right? And the laser beams are gonna reflect off of stuff and come back.
And based on the time that it takes to come back, you know how far away things are, right?
And so essentially, you're just gonna have this really high speed thing shooting out laser beams, and the laser beams will reflect, and they will tell you where things are. And so LiDAR is nice because it's less affected by things like weather conditions than like cameras. Right? And so basically, it just does the thing that I just showed. It's like shooting out light beams, seeing how far it takes to go and come back, right?
So what that essentially means is that a LiDAR is, where'd it go? Yeah, so
A LiDAR is essentially giving you a particular, like ZT is going to be like a distance, right? So it's going to say, given where you are in the world, the laser scan is going to be a distance of, in a particular direction, how far is the obstacle, right? And given a particular map and where you are in the world, you're going to have some probability over what the distance is going to be in one direction, right? And you're going to have, many different laser beams in many different directions, and each of them will have a likelihood function. And so the point here is that ZTs are going to be distances, and
how far away is something in a direction?
XT is going to be positions, and M is going to be over. And so that's your sensor model.
Your sensor model is gonna give you a likelihood of what is the distance, what is the probability that it returns a particular distance in a particular direction. Right, but if I just had one
Laser beam, that's not going to tell me that much. So I'm going to have a bunch of laser beams, right?
and so typically a motion model is
Going to be not just one laser beam, but you're going to have K different laser beams, right? You're going to have from 1 to K,
and those laser beams will go in every direction. And then the likelihood is going to be
the product of the individual sensor models for each of those laser beams, right? So almost think about you have a car somewhere, you're shooting out laser beams in every direction, right? And depending on where you are and which direction you're facing, it's going to give you different distance, right? And you're going to take the product of all of those likelihoods, and that's going to give you the product that you got all of those ratings to get them. Yes? Okay, so this is not always true. I jumped from here to here. It's not always true.
Can someone tell me what's the assumption?
Yeah. That they're independent, perfect. So we're assuming that these laser beams are independent, right? When are they not independent?
When is that like a bad assumption?
Well, I guess I had the answer. But yeah, when are they not independent? Like what can break this? Take a wild guess. Yeah. Yeah, like, they like interact.
Yes, when they interact with each other or they're pointing in the same, very close to each other, they're going to interact with each other and they're no longer independent, right? So they, like, if you have things that are like
Interfering with each other, then the readings are no longer independent. So if you double count them, then this independence doesn't hold, so you get overconfident.
Well, right, so you want to be careful that you don't double count things and
Your independence assumptions hold. And so typically what you do is if you have a LiDAR facing in all directions, you subsample the LiDAR beam. So you don't have like things that are extremely close to each other because they're likely to interfere. And so instead you have things that are spaced out. And so imagine you shot up like a 500 laser beams, you choose every fifth one.
right, so it's quite simple, but
Essentially what you want to do is you want to shoot these laser beams out in different directions, treat them as independent. And then we want to define what is this likelihood for every laser beam.
Are ever like effects?
Yes. Yes, and that the way you kind of deal with that is you change the time step at which you do these updates. So you try to do more high frequency updates so that within the time period that you're considering, it doesn't change.
It's never the case where like cars moving so fast. No, that one.
Not in this car,
Okay.
but it's like going at the speed of light.
Yeah. Right. So this is like much more of a problem in things like sonar, right? Because sonar is like speed of sound. And so that's going to be more of a problem. Then you have to like account for your own motion there.
Okay, so all that a LiDAR is, it's time of flight in a particular direction. We're going to consider a single beam and try to define what the probability is that you get a particular reading, CTK, given you're at some position xt, and you have some map M, right? Okay, so the first and simplest thing you can do is, you know the map, you know which way you're shooting the laser beam, right? You can like just use geometry to compute the distance between the car and the map, the closest thing in the map, right? So given an xt, given a map, you just compute the shortest distance to an obstacle, and that's your ZT, right? That's your ZTK. Why is that? Why is that not a good idea? Just to like treat that as a fixed number. You have the map. So if you have the map, you just put your robot in the map, you compute the distance in the map to a fixed obstacle, right? The closest obstacle, that's your ZTK. So why is that not a good idea? Object is moving, your sensor might have noise, there's occlusions, there's, things that you didn't model in the world in your map, or your map might be wrong. So because of like sensors being wrong, modeling being wrong, maps changing, you have to be probabilistic, right?
And so what we're going to figure out is like, what are the sources of noise in a sensor model?
And how do we change this thing to be probabilistic to model realistic sources of noise? Yes. So the four types of things we're going to try and deal with. The first is just some noise in sensors, right? You just have like
Gaussian noise in the world, things are not perfectly accurate, right?
voltage errors, like sometimes the surface properties are a little different, right? And that affects how much things reflect. And so we just want to deal with local measurement noise. The second thing we want to deal with is, let's say you had a map of the world and a person walks through the map, right? It shouldn't totally screw up your system. And so you want to have some likelihood of unexpected objects that show up in your map. The third thing we want to deal with is sometimes sensors just fail, right? Like a transparent object or, things that reflect things weird, right? Or things that absorb light. You're going to have sensor failures, right? And so you want to be able to model some number of sensor failures and kind of be robust against them. And lastly, in general, it's good to have some random measurements. Sometimes your sensors malfunction, sometimes they return crazy numbers. And so we're going to try and have these four types of errors, right? We're going to have local noise, unexpected objects, sensor failures, and random measurements.
Yes. Okay. So
We're just going to go through them real quick. All that local noise is saying is that if this was the distance you computed to the map, ZTK star, right? That's the distance you computed the perfect map. Just add some Gaussian noise to it, right? So it's saying that your thing might be a little wrong, add some Gaussian noise to it. That's local noise. Yes, so that's the probability that you might have this local noise.
the second thing you're gonna
Deal with is you're going to deal with unexpected objects. Right? So sometimes
there might be unexpected objects, and so the distance that the map tells you might not be the distance that you actually see in the world. Right, so you want to have some likelihood that there's unexpected objects. And so the way we're gonna try and do modeling of unexpected objects is we're gonna use an exponential distribution. And so there's a nice intuitive explanation of why you need an exponential distribution, right? It's basically saying that if there's an unexpected object, it's only gonna matter if it's closer than the obstacle, not further than the obstacle. Because if it's further than the obstacle, who cares? It's gonna bounce back anyway. So it's only gonna matter if it's closer than the obstacle. But if you have multiple, it's going to be biased towards things that are closer, right? Because it's going to say that if you have an obstacle that's closer, it'll return a value. If an obstacle that's further, it has to not exist at the first point and exist at the second point. And if you have an obstacle that's further, it has to not exist at point 0 and point 1 and has to exist at point 2. And so it's exponential because you have to say that for an obstacle to be somewhere, it has to also not exist at every point of the point. And so basically, whenever you have unexpected obstacles, the details are not that important, but you want them to be higher likelihood of being closer and then lower likelihood of being further. Right? And the idea is just that for something to be detected like at this distance, it has to not have been detected at all of the places before. So imagine you're doing a coin flip. It has to have flipped tails at every step before, right? And so that's why it's going to be an exponential. Does that kind of make sense? The details are not that important. You're going to do something simpler in your project, but just kind of think of it as you want things to be higher likelihood of being detected closer. Yes? Okay, so that's the second type of noise. And the third two are extremely easy. Basically, sensor failure says, okay, you thought it was going to be here, but sometimes the sensor is just going to completely fail. And so it's going to return maximum value. That's just like the sensor was supposed to detect it. It did not detect it because the beam didn't get reflected, it got absorbed or something else, right? And so you're just going to have some likelihood that it returns the maximum value. That's the third type of error. And then the last type of error is that you just have some likelihood that you return a random value. And so you have some likelihood that you have uniform over the whole range. So just like a uniform distribution between the whole range from 0 to the maximum. Okay? So the four types of errors are local Gaussian noise, right? Unexpected objects. Local Gaussian noise is just a Gaussian. Unexpected objects is something that's high likelihood at the start and then goes down. You have sensor failures, which is just going to give you the maximum. And then you're going to have some amount of uniform random measurements, right? And you're going to have your likelihood of the particular value here, right? Just being some weighted sum of these four types of errors. Right? So you can have four different types of errors. You're going to have some proportion of weights for each of them, and you're going to kind of sum them up. And for every system, you have to identify what these values are going to be. Right? And that's going to be some amount of parameter tuning that you have to do. But generally, all our sensor models are going to be of this form. And so just think of it as Gaussian plus exponential plus maximum plus unit. Okay, so what we kind of covered here is we covered motion models, right? We're going to use some physics. We're going to add some noise to it. Right? Instantaneous center of rotation, some numerical integration, noise. And then we covered sensor models, which is the geometry and shooting beams in different directions, plus four types of noise, right? And that's going to be the motion model and sensor model for your homework. And everything else is like less relevant, right? So we've re-explained all of these in the homework as well. So please go home, try to work these out, come to office hours. We want you guys to really understand this very well. So yeah, that's it for today. We'll try to cover Kalman filtering and stuff next class, but yeah, thank you. Have a good long weekend.